Alrighty, in this video we are going to be talking about Lagrange. So let's say that we have something that isn't alternating in terms of my approximation. And whenever I mean approximation, we are going to be using a Taylor approximation here, since we are going to most likely be approximating function values. To approximate function values, we are going to have our Taylor polynomial, and then my original function that I'm approximating. Well, if I take that difference, that's going to give me my remainder. Now, that remainder, of course, is going to be my error. In that case, we have Taylor's theorem right here, which basically gives us my function plus the Taylor polynomial plus the remainder. Now, the remainder here is going to be my next derivative. So notice how I have f of n to the x over n factorial times x minus c to the n. Well, my remainder is going to be that next derivative at z, and we'll talk about more about what z is, x minus c to the n plus 1 over n plus 1 factorial. Now, z is going to be very important because z is going to be a number between x and c, and this is going to make a maximum in terms of that n plus 1 derivative. So essentially here, we're trying to find, which is going to be the hardest part, we're going to find a value z between x and c so that this lovely thing right here is a maximum. How do we do that? Well, we're just going to have to either think about it logically in terms of our derivatives, actually find it, or if they give it to us. All right, so x is going to be my estimate, c is going to be my center, n plus 1 is going to be my next term, and then, of course, we want to find the maximum value of n plus 1 derivative between x and c. All right, so number one, we are going to be using an upper bound for error approximating e to the negative 1.5 with a Lagrange polynomial of degree 4. Now, can I use alternating series error for this? Yes, because you'll notice that e to the negative 1.5, this is going to be alternating if I were to build that series. However, because my emphasis is going to be on Lagrange today, I'm not going to be building the series, and I'm only going to be focusing with e to the x here. So my error in this case is going to be less than or equal to the fifth derivative at z, whatever that is. X is going to be my estimate, which is negative 1.5. C is my center. And then I have a degree of 5 over 5 factorial. Now, we're using e to the x as my function approximation. If my function is e to the x, this is going to be very good for us because guess what? The derivative of e to the x, no matter what that derivative is just going to be e to the x, which is really good because now I get to say that the fifth derivative of e to the x is just e to the x. Wow. Which is like this. Now, the reason why I kind of drew it is so that we could visualize where negative 1.5 is and where 0 is in terms of my graph. Because remember that I want to find the maximum value for this right here. Notice how negative 1.5 is like right here, and then 0 is right here. So my maximum value is going to be at 0. So now, instead of z, I know that that value is going to be 0. And my fifth derivative at 0 is just going to be 1. So now my error is going to be less than or equal to 1 times negative 1.5 to the fifth over 5 factorial. And there you go. Now, what is that on the calculator? I don't know. You just got to figure that out on your own since this is no calc. And I didn't do that on my thing. Now, number one was kind of relatively easy just because the derivative of e to the x was just e to the x. Later, you'll see on number three, though, that's not going to be the case for the other ones because your derivatives are going to get pretty nasty. Now, it also might be helpful in terms of, let's say, using power series to help us for a couple of these problems, which we would do on number three. Number three says, what's the maximum value of the error in approximating ln of 1.2 with a Taylor polynomial of degree 3 centered at x is equal to 1? Okay, so do I need to make up that Taylor polynomial? No. However, I do need to find the derivatives of it because essentially I am going to need to find the fourth derivative because I need the maximum at z for my fourth derivative. X is going to be 1.2. My center is going to be 1. Since this is a degree 3, this means that my degree is going to be 4 over 4 factorial. All right, now here comes the hard part, figuring out what my fourth derivative is. F of x is going to be ln of x. F prime of x is going to be 1 over x. F double prime of x is going to be negative 1 over x squared. The third derivative is going to be 2 over x to the third. And then the fourth derivative is going to be negative 6x to the fourth. Okay, so now remember that z is going to be between 1.2 and 1 right here. So if I'm going to think about this in terms of negative 6 over x to the fourth and what that looks like, it kind of looks like 1 over x squared. So remember that 1 over x squared looks like this. But then, because we have a reflection over the y-axis right here, because it's a negative, my function is going to look something like that. Okay. Now, we want to find the maximum value, no matter if it is negative, because it's just the maximum, so the maximum absolute value. In this case, if I were to look at 1, 1's probably going to be right here, and 1.2 is going to be a little bit higher than 1. So here, if I were to think about this means that my maximum is going to be at 1, just because that's going to be my maximum, the absolute maximum value, if that makes sense. So now, if I were to do that, I am going to find my fourth derivative at 1. I should have done that right here. Fourth derivative at 1. And in that case, that is going to give me negative 6. But remember, since it is technically the absolute value, I'm going to use positive 6. Just so that I have it for the LOLs. So this tells me that my error is going to be positive 6 times 0.2 to the fourth over 4 factorial. What is that? Plug it into the calculator and call it a day. Before we move on to number 4, like I said earlier, we are going to probably write this in terms of a power series. Why? Well, it's because we don't know what the nth derivative of this is. And in order to find the nth derivative, it might be easier if we use a power series to help us, because we're going to need that for number 4. You'll see why in like 2 seconds. But let's just go ahead and figure out what my derivative is in this case. Okay, so My nth derivative, I have ln of x, 1 over x, negative 1 over x squared, 2 over x cubed, and negative 6 over x to the fourth. You'll see that I'm always going to have x to the n, and I'm also going to have 1 to the n, because it's going to be alternating. The problem is I don't know what to do with my coefficients, because it's 1, then 2, then 6. If I were to look at my fifth derivative, that's going to be 24 over x to the fifth. If I were to look at my sixth derivative, that's going to be negative 120 over x to the sixth. Which hopefully you might notice a pattern in terms of, hey, these are my factorial numbers. 1, 2, 6, 24, and 120. So I'm going to have some sort of factorial going on. Now, is it going to be n? Let's check. If it's n, then 1 factorial is just going to be 1. That's great. 2 factorial, however, is 2. And 3 factorial is 6. And 4 factorial is 24. 5 factorial is 120. You'll notice that this means that in order to get my correct coefficient right here, I'm probably going to have to subtract a factorial so that whenever I do it, I get, let's say, 6 minus 1 factorial, or 5 factorial, which is 120. 5 minus 4 factorial, 5 minus 1 factorial is 4 factorial, which is 24. 4 minus 1 is 3. 3 factorial is 6. 2 minus 1 is going to be 1. 1 minus 1 is going to be 0 factorial. How many ways can we choose something 0 times? 1. So that's going to give us that thing right there. So that tells me that my nth derivative is going to be negative 1 to the n minus 1 factorial over x to the n. Now, why did we do that? Well, let's look at number 4. Number 4 is a calculator active question because I didn't say no calc. It says determine the degree of the Taylor polynomial centered at x is equal to 1. That should be used to approximate to ln of 1.2 so that the error is less than 0.001. Error is going to be less than or equal to the next derivative. And that's my problem. I don't know what my next derivative is because I don't know what my degree is. And I don't even know what z is. That's going to be between 1 and 1.2. That's all I know. I don't know anything else. I still know that this right here is just going to be 0.2 so. And then I'm going to have n plus 1 factorial. And this right here eventually needs to be less than 0.001. If my nth derivative is this right here, then this is going to tell me that my n plus 1 derivative is going to look like negative 1 to the n plus 1 n factorial over x to the n plus 1. Now, since we are working with z, though, this is going to give us error is less than or equal to negative 1 to the n plus 1 n factorial over z to the n plus 1, since I'm not working with x here. This is going to be 0.2 to the n plus 1, and then we have n plus 1 factorial, and this is going to be less than 0.001. All right, I'm going to clean this up a little bit. Notice how we have n factorial right here and n plus 1 factorial right here, and we know that n plus 1 factorial is n plus 1 and n minus 1 and so on. So that means I'm only really left with n plus 1 in the denominator. So now I have 0.2 to the n plus 1 over z to the n plus 1 times n plus 1 is less than or equal to 0.001. I did get rid of the -1 to the n plus 1 because that's just going to be 1 if we take the absolute value of it. Now, once we do that, I have another problem. I don't know what z is because it's z to the n plus 1. Even though you don't know what z is, that's okay, because remember, that's going to be some arbitrary value, and that's going to be definitely less than 0.2 to the n plus 1 over n plus 1. So I just got rid of that, just because we know that no matter what, this right here is going to be larger. I'm going to focus on this now just because now I could technically solve for n and find out what my value of n is. In this case, if you were to use the handy-dandy calculator on this, you're going to get n is greater than 2.512, which means that n has to be greater than 3 for our error to be less than 0.001. So that we get that. All right. In the next video, we are going to be looking at graphs, tables, other equations, and then we'll see where that takes us.